2y over dx. I mean, times dy of dx.
And the right-hand side?
We're taking the prime of r squared, right?
Oh, yes. I'm sorry. Yes. Who cares? It's a constant. We're only talking about x and y. R is just any number. Good. So then dy over dx, simplify both sides by 2. Dy over dx, I move x to the other side, negative x, and divide by y. So this is negative x over y. Now I need to determine this. They're separate, completely separate. So we had ax plus by equals 0. Ax plus by equals 0. Good. So let's differentiate implicitly. The left-hand side.
Why is r squared, why is that a constant? Why wouldn't that same logic apply to x or y?
So in Calc 1, we can only have functions of one variable. So if this is the function and this is the variable, this must be a constant. And we said that if we cannot have a circle with 3 variables. So it's x and y, and this has to be a constant, and it can be 1, it can be 1.5, it can be 0, that would be a point, and so on and so forth. 0, it shouldn't be considered because that would be just 1 point. So if this is not a constant, then we're not talking about circles. Yes, I can. You have to wait till Calc 3 with functions of more than one variable. So here we can have more than one variable. If this is the function, this is the variable. Anything else is a constant. Good. So let's differentiate here and determine dy over dx for the second curve function in this case. Anyone?
Is it a plus b dy dx?
Excellent. Equals 0. So then it's a moved, negative a over b. So dy over dx equals negative a divided by b. Great job. Constant, it's a line. Of course, we expect the derivative or the slope to be a constant. Very good. Now, final step. I know it's a long problem. Final step. Check. This is page 10. Check for each point of intersection that m1 times m2 equals negative 1. Condition for perpendicularity. Condition for perpendicular tangents. Okay, so I'm going to say for point A has br over the square root, comma, negative ar over the square root, a squared plus b squared, a squared plus b squared. And also dy over dx for the first one. I'm just copying them so I can remove that page. So I have to determine this, negative x over y, x over y. Whatever I get times this has to equal negative 1. If when I evaluate negative x over y for this point times this, it does not give me -1. I don't have to look at the second point. I'll say they're not orthogonal trajectories of each other. Because at one point of intersection, they're not perpendicular. The tangents are not perpendicular. I don't have to look at B. But if I get the result that is -1, the product of these two slopes after I plug in, here I don't have anything to plug in, but here I have this over this in here. Then I move on to B. If for both I get -1, for point A of intersection and point B of the other intersection, I get -1, then I'll say it's clear they are orthogonal trajectories of each other. So -x over y. So I want to determine the first one. That's the only one I need. The other one is a constant for any point. So I have negative. This at the top, BR, and I'm not going to even write the square root because they will change. They will go away because they are the same. When I put this over this, the denominators by flipping will go away. Then I simplify and I get B over A. Yes, this times this, M1, slope of first one, times the slope of the second one at the first point is -1. Yes. So now I have to check for B. B was